Hello, everyone. So last time we were still doing number theory. And we looked at the definition of GCD of two numbers, or greatest common divisors. Greatest common divisor of two numbers. So this one was defined. And as you can guess from the name, greatest common divisors means between two numbers, A and B, means you have to look at the common divisors of A and B, positive common divisors of A and B, and then choose the greatest one. And then we provided one algorithm to find GCD and also LCM. So LCM was also defined. And we said that, if you want to find GCD and LCM, one way to do that is that you can factorize A and B into prime factors. And then look at for GCD, you have to basically look at the common factors, common prime factors, and use the smallest power, and then smallest power between A and B, and then multiply them. For LCM, you have to use the maximum power between all the prime factors that appear either for A or B, and then multiply them. And then we also looked at Bezot's identity, which was saying that if A and B are relatively prime, relatively prime means GCD of A and B is 1. Then AT, let's say, plus BS equals 1 for some integers T and S. So relatively prime means GCD is 1. So that's another name for when GCD is 1, GCD of two numbers is 1. We say that those two numbers are relatively prime. And under that circumstances, we can say that AT plus BS equals 1 for some T and S. So in other words, some linear combination of A and B is going to be 1 if A and B are relatively prime. Now today we want to start the section 4.4, which is solving congruences. So the goal is to solve, let's say, AX congruent, let's say B mod M, where A and B are integers and M also integer, and we want to solve for X. So means finding all integers X that satisfy AX congruent B mod M. So solving an equation means what? So it means finding all values of X that satisfy the equation. Or similarly for inequality, solving an inequality means finding all values of X that satisfy a given inequality. Satisfy means when you replace X with those values, the inequality holds or the equation holds. So similarly, congruence. Solving a congruence means finding all values of X that that satisfy a given congruence, meaning that when you replace X with those values, the given congruence holds, basically. So before giving a recipe about how to solve a given congruence, so let me give you a simple example. For example, let's say you want 2X, for example, congruent 1 mod 3. So what is the solution for this? So you may tell me that, okay, if it was, for example, 2x equals 1, then we have to multiply both sides with 1/2, and then we get x equals 1/2. But 1/2 is not an integer, right? So in number theory, please remember that we always work with integers. So we normally won't accept fractions. So still we can use that idea. I will tell you in a few minutes that we can still use the idea that we multiply both sides with inverse of 2, but then inverse of 2 will not be 1/2 anymore. I'll explain this. But before finding an algorithm about how to solve a given congruence, let's see whether we can at least guess a solution for this congruence, let's say by inspection or just checking numbers one by one. So let's say you want 2x to be congruent 1 mod 3. So what should I choose as x? So this one is solution for this. So let's just do it by inspection, just to guess for this example, and then I'll give you an algorithm how to solve a general case. Well, for example, if x is 1, if x is 1, 2 times 1 is 2, which is not 1 mod 3. 2 is not 1 mod 3. But let's say if x is 2. If x is 2, then 2 times 2 is 4, right? Which is 1 mod 3. 4 is 1 mod 3 because 3 divides 4 minus 1. Do you remember the definition of congruence? If we say A is congruent B mod M, means M divides the difference between A and B. So here, 4 is 1 mod 3 because 3 divides 4 minus 1. Okay, so at least one, so we at least found one solution, which is x equals 2. But do we have more solutions? Well, in the linear equation, ax equals b, we know that we have, at most one solution, or exactly one solution if a is not 0. But what about this case? Because here we don't have an equality, we have congruent. See, 2x congruent 1 mod 3. So do you think we still have one solution, or maybe we have more? So what about, for example, 5, x equals 5? How much is 5? I mean, how much would be 2x if x is 5? So 2x would be 2 times 5, which is 10, and that's 1 mod 3. Again, because 3 divides 10 minus 1. So see, we have more than one solution. We already found 2 solutions, x equals 2 and x equals 5. So probably we are going to have more solutions. So let's see whether we can find all the solutions for any given congruence. So we start by finding an inverse of a given number A mod M. So remember that we said that, as you know from high school, for example, 2x equals 1, to solve it, you multiply both sides with 2 inverse, and then you get x equals 1/2. So we want to apply the same idea and multiply both sides with inverse of A. Let's say if our equation is or our congruence is AX congruent B mod M. We want to multiply both sides with inverse of A, but inverse of A is the inverse mod M. What is the meaning of inverse mod M? So let me first give you the definition of inverse mod M, and then I'll tell you the recipe to find inverse of a number mod M. So the numbers A and B are called inverse of each other mod M if AB equals BA equals 1 mod M. Or one of them, if AB is 1 mod M, of course BA is also 1 mod M, because of course AB is always equal to BA. So you can write this, or you can just to make the definition simpler, maybe I can just say AB is 1 mod M. So still similar definition that you know from middle school for inverse of a number. So AB, previously in middle school, you would say AB equals 1. And in that situation, you would say A and B are inverse of each other. But here, because everything is, instead of equality, we have congruence mod M. So A and B are called inverse of each other if AB is congruent 1 mod M. Now, let's see which numbers have inverse mod M. So theorem. So suppose that, so let me, I can divide into two parts. Part A, if GCD of A and M equals 1, then A has an inverse mod M. Part B, if GCD of A and M is not equal to 1, then A does not have an inverse mod M. So let's see how we can prove this proof. So if GCD, so what is the assumption in part A? So this theorem exactly characterizes which numbers have inverse mod M and which numbers do not have inverse mod M. So if GCD of two numbers is 1, then A has inverse, and if GCD is not 1, A does not have inverse. So very simple characterization that determines exactly which numbers have inverse and which numbers do not have inverse. Now to prove the theorem for part A. So what is the assumption in part A? Assumption is GCD of A and M is 1. Now by Bezot's identity, see, we said about Bezot's identity, which says if two numbers have GCD 1, then some linear combination is 1. Linear combination of them is 1, meaning that like AT plus BS equals 1. And right now I have A and M, GCD of A and M equals 1. So that means AT plus MS equals 1 for some integers T and S. Okay, and then I want to show that A has inverse mod M. So what about if I look at this equality as a congruence mod M? Of course, if two numbers are equal, they're congruent as well. right? Equality is stronger than being congruent. So for example, the other way is not correct, of course. For example, 12 and 6 are same mod 3, but of course 12 and 6 are not equal, right? But if two numbers are equal, then of course they are congruent. So right now I have two numbers which are equal. So of course they're congruent as well. So that means AT plus MS congruent 1 mod M. But how much is MS mod M? MS is 0 mod M. If a number is a multiple of M, that means that number is 0 mod M, right? Because again, think about the definition of congruent. MS is 0 mod M means what? Means M divides the difference between MS and 0, which means M divides MS. And of course, that's true, right? M divides MS because MS is a multiple of M. So MS, I can replace it with 0 mod M. I'm looking at everything as mod M. So then I get AT congruent 1 mod M, and that means A has an inverse mod. I wanted to show that A has an inverse mod M. And what is the meaning of having inverse mod M? It means there's another number that when I multiply those, I get 1 mod M. So there you are. So I showed A has inverse mod M. Now for part B, if GCD is not 1, then A does not have an inverse. So I want to show that A does not have an inverse mod M in this case. So what? How about if I use proof by contradiction? So for part B, proof by contradiction. Suppose that A has an inverse mod M, right? I want to show that A has no inverse mod M. So let's assume it has an inverse mod M. Then there exists T such that AT is mod 1 is 1 mod M, right? That's the meaning of inverse. And what does that mean? That means M divides the difference between AT and 1, right? That's again definition of congruence. And then what does that mean? That means AT minus 1 equals MS for some integer S. That's the meaning of, one number divides another number. And then this means 1 is equal to AT minus MS. Okay, now remember, I want to reach a contradiction. How can I reach a contradiction? 1 is equal to AT minus MS. Of course, I have to use my assumption somehow, right? What was the assumption? Assumption in this case was GCD not equal to 1. How can I use this assumption to reach a contradiction here? GCD not equal to 1 means GCD is bigger than 1, right? So I can write A, let's say, as the form dA prime, and M in the form, let's say, dM prime with D bigger than 1. So GCD, and here with there's a D here is GCD, which is bigger than 1. GCD bigger than 1. So I'm calling GCD as D here, denoting it by D. So then that means D is a common divisor for A and M, right? It's of course greatest common divisor, but in particular, it's the common divisor for A and M. So I can write A in the form dA prime and M in the form dM prime. D is a common divisor for A and M, right? And GCD not equal to 1 means it's bigger than 1. So that means D is bigger than 1. So this is what I can conclude by my assumption, which says GCD is bigger than 1. So now if I replace A and M with these expressions, what do I get? I get 1 equals dA prime T minus dM prime S. And that means 1 is equal to D times A prime T minus M prime S. And this means D divides 1, and this is a contradiction. We wrote 1 as D times some other integer, right? So that means D is a factor of 1. But the only positive factor of 1 is 1 itself, but D was bigger than 1. Since 1 has no factor, D bigger than 1. We wrote 1 as a number bigger than 1 times another integer. Of course, that's not possible, and that's a contradiction. And well, that's it. So that this contradiction, thus we can conclude that A and M, let's say that A has no inverse in this case. Okay. Okay, now let's see in practice if we have two fixed integers, how we can find out whether, two fixed integers, let's say one as A and one as M, how we can find out whether A has an inverse mod M, and if it has, how can we find the inverse? So let's start with an example. Determine whether 101 has an inverse mod 4620, and if it does, find its inverse. Okay, so this theorem tells us the recipe to find out whether a number has inverse or no. We have to look at the GCD of A and M. If GCD is 1, then A has inverse. If it's not 1, it doesn't have inverse. Okay, so to answer this question then, so we need to, solution, we need to find GCD of 101 and 4620. So how can I calculate GCD of two numbers? If you remember, we saw the algorithm last time. We have to do the long division, right? So we saw the algorithm to find GCD of two numbers, which we called it a Euclidean algorithm, right? Last time. So we have to do the long division. I will start with 4,620 is 101 times some quotient plus some remainder, right? So the quotient, if you do the long division, you will see that the quotient is 45 and the remainder is 75. Now in the next step, I have to divide 101 by 75. 101 75 times 1 plus 26, right? Because we saw that, if I'm calling these M and A. So M and A, GCD of M and A was same as GCD of M and this R. So that's why we divide M by R in the next step. And then again, GCD of these two numbers are same as GCD of these two numbers. So then in the next step, we divide 75 by 26 and we continue, right? So we saw these steps last time. So 75, if I divide it by 26, 26 times 2 plus 23, and then 26 by 23, 26 is 23 times 1 plus 3, and then 23 and 3, which is 7 times 1, 7 times 3, quotient is 3, plus 2, and then 3 and 2, 3 is 2 times 1 plus 1, and then 2 and 1, 2 is 2 times 1 plus 0. Once the remainder is 0, then I will finish or end of algorithm. And what will be the GCD? GCD will be this number here. So this number is, so 1 is GCD of 2 and 1, which is same as GCD of 3 and 2, right? If you go backward, so 1 is GCD of these two numbers, but then GCD of these two numbers is same as GCD of 3 and 2. And then, we go all the way backward until we get GCD of the original two numbers that we had. You go step back and then back and then back and then back and then back, and then we get these two, which is 4,620 and 101. So GCD is 1. That means the number has inverse, right? Remember the theorem said if GCD is 1, the number has inverse. If it's not 1, it doesn't have inverse. So by theorem, part A, 101 has an inverse mod 4,620. Okay, now our next job is to find the inverse of 101. So we showed that 101 has an inverse mod this number. Now we want to find it. So next, to find the inverse of 101 mod 4,620. Note that the proof in theorem part A shows that we need to write 1 as a linear combination of 101 and 4,620. So let's look at the proof of theorem again, part A. We wanted to show that if GCD is 1, then A has an inverse. So we started with, our starting point was this equation, AT plus MS equals 1. And then we looked at it as a congruence mod M, and then we got AT congruent 1 mod M. So the key point is this equation, AT plus MS equals 1. So that means if we can write 1 as a linear combination of A and M, then the rest is easy. Just look at the equality as a congruence mod M, and then you will find the inverse of A. So the key point is to find integers T and S where 1 is equal to AT plus MS. So that's why I said here that the proof shows that we need to write 1 as a linear combination of 101 and 4620. In other words, find T and S where 1 is equal to 101 times T plus 4620 times S. Now, if we look at the Euclidean algorithm, we can write 1 as a linear combination of A and M, in this case 101 and 4620. So we can do so. I'll charge the pencil. So we can do so by using Euclidean algorithm above. Okay. So 1. So look at 1. We want to write 1 equals something, right? So first of all, if you look at this equality here, I can write 1 as 3 minus 2 times 1. So let's start with that. 1 times 2. And then if you look at the equation above this, 2 can be written as like 23 minus 7 times 3. So 3 minus 1 times 23 minus 7 times 3, which is same as 3 minus 1 times 23 plus 7 times 3. Now 7 times 3 and plus 3 is 8 times 3 minus 1 times 23. Now if we look at the equation above this, 3 could be written as 26 minus 23 times 1. So 8 times 26 minus 23 times 1 minus 1 times 23, which is 8 times 26 minus 8 times 23 minus 1 times 23. That's 8 times 26 minus 9 times 23. Then again, let's go one step above. 23 itself could be written as 75 minus 26 times 2. 75 minus 23 times 2 minus 9 times 23. Minus 75 minus 26 times 2. So minus 26 times 2. And then this one we can write 8 times 75 minus sorry, I think I made a mistake. 23 could be written as 75 minus 2 times 26. So 23 is here. I can replace this with, I have to replace this guy with. So 8 times 26 minus 9 times 23 could be written as 75 minus 2 times 26. Is that okay this time? 2 times 26, yeah. So now if you simplify this, 8 times 26 minus 9 times 75 plus 18 times 26. Now 8 times 26 and 18 times 26 is 26 times 26 minus 9 times 75. And then 75. So we use this equation. And then 26 can be written as 101 minus 75. 101 minus 75. 101 minus 75 minus 9 times 75. So this is 26 times 101 minus 26 times 75 and 9 times 75 is 35 times 75. And then last step, 75 could be written as, I'm here now, 4,620 minus 101 times 45. 4,620 minus 101 times 45, which can be written as now this one we can write it as 1,601 times 101 minus 35 times 4,620. Okay, so we wrote 1 as a linear combination of A and M. Then again, remember the proof. After we wrote 1 as a linear combination of A and M, we looked at the equality as a congruence mod M. So that means 1 mod M is 1,601 times 101, because the other term becomes 0, right? The other term is a multiple of M. M here is 4,620. And a multiple of M is always 0 mod M. Well, there you are. We got the inverse of 101. So that means inverse of 101 mod M is 1,601. Because 101 times that number gives 1 mod M. Okay. So now one exercise that you can try to prove is show that if GCD of A and M is equal to 1, then the inverse of A is unique mod M. We already proved that in theorem part A that if GCD is 1, inverse of A exists. Now you want to show that the inverse exists, which we already proved, and is unique mod M. What is the meaning of unique mod M? Unique mod M, i.e., if let's say B and C are inverses for A mod M, then B and C are congruent mod M. So if I say that the inverse is unique, means whenever you have two inverses, then those two inverses must be equal. But I did not say that the inverse is unique. I said that inverse is unique mod M. What's the meaning of this? Means if you can have two inverses which are not equal, but they are equal mod M, meaning that they're congruent mod M. So if you have two inverses, if you want to show that a solution is unique, you have to show that if there are two solutions, then those two solutions must be equal. But if you want to show that the solution is unique mod M, it means you have to show that if there are two solutions, then those two solutions are congruent mod M. Okay, then remember our goal was to solve. So next, to solve AX, let's say congruent B mod M. How can we do this? So if GCD of A and M is equal to 1, multiply both sides by inverse of A mod M. And then you will find X. So let's look at an example. Let's say, find all solutions of, for example, 101 times X. And let's say congruent 3 mod 4620. So since GCD of 101 and 4620 is 1, which we showed above, we can multiply both sides by 101, inverse of 101, mod 4620, namely, what was that number? Inverse was 1601. Derived above. So then you get 1620 times 101 times X, congruent 3 times 1620, and then mod 4620. So 1601, 1601, not 20, 100. Now this part is 1 mod 4620, right? So that means 1 times X, 3 times 1601. So that was the point, right? To get 1 times X, which gives us X, and we want to find X. Now 3 times 1000 mod 4620. Now 3 times 1601 is 4803. So that means X is mod 4803 mod 4620. But what is 4628? What is 4803 mod 4620? Means we need to find the remainder, right? So 4000, let's say 4803 minus 4620, that will be 183. Okay, so the solution is basically 183, right? So these two you can easily check that 4,803 can be written as 4,620 plus 183, which means 183 and 4,803 are congruent mod 4,620. So what is the solution? So the solution, the unique solution mod 4,620 is X mod 183 congruent 183 mod 4,620. So you can write your final answer like this. Remember, we said that the solution is unique mod M. Or if you want to write your solution as an equality or using set notation, so in other words, a set of all solutions is 183 plus, let's say 4,620 times k, where k comes from the set of integers. So which numbers are 183 mod 4,620? Any number of the form 183 plus 4,620 times k, where k comes from z, right? Well, for example, 183 itself, of course, is congruent 183. But if I add, for example, 4,620 to my number, still the number is congruent 183, right? Because 4,620 is 0 mod 4,620. And also any multiple of 4,620 is 0 mod 4,620. So if I add 4,620 itself or any multiple of it to my solution, I still get a solution which is congruent 183 mod 4,620. So if you want the solution of the set of all solutions, you can write it in this form. So I can also mention here that x equals, let's say, a plus bk if and only if x is a mod b, right? So these two are equivalents. Now my a is 183 and my b is 4,620. But whenever x is a plus bk for some integer k, I can say that x is a mod b and also conversely. Okay, so please remember that we are done with solving the congruence in the case where GCD of A and M is 1. So let me clearly say here that this is, let's say, case 1. If GCD of A and M is 1, then we saw how to solve the congruence. Now, case 2, if GCD of A and M, let's say, equals D is bigger than 1. Now, how can we solve the congruence in this case? Again, I'm going to divide this case again into two sub cases. So case 2.1, if D does not divide B, if D is not a factor for B, then in this case, we can say that AX equals B mod M has no solution. Why? Because since otherwise, if this has a solution, then let's say AX0 is equal to B mod M for some integer, let's say x0, then what can I say? Then I can say that M divides AX0 minus B, which means AX0 minus B equals MK for some integer K. And then A, we can write it as, let's say, dA prime. M, we can write it as dM prime, because remember, D is the greatest common divisor of A and M. So that means D is a factor for A and also a factor for M. So that means dA prime x0 minus B equals dM prime K. Now if I take B to the right side and the other term to the dM prime K to the left side, I get B equals dA prime x0 minus dM prime K, which means D times A prime x0 minus M prime K. And this is a contradiction. Why? Because my assumption in case 2.1 was D does not divide B, which means D is not a factor for B. But right now I wrote B as D times some integer, right? So that means D is a factor for B, right? So contradiction, it was a contradiction with D does not divide B. So that means in this case, AX equals B mod M has no solution in this case. Okay, so for example, let's say 10x equals, let's say, 3 mod 15. So this one has no solution since GCD of A and M, GCD of 10 and 15 is 5, and 5 does not divide 3. 5 is not a factor for 3. Therefore, we are in case 2.1, according to case 2.1 above. And therefore, this congruence has no solution. Now, the only case that is still left, case 2.2, if D divides B, so which means if D is a factor for B, what should we do in this case? So I want to give you a remark here. Note, if GCD of A and M equals 1 equals D, then we can write let's say A equals dA prime and M equals dM prime, where GCD of A prime and M prime equals 1. So whenever GCD of two numbers is D, we can write A as dA prime, M as dM in the form dM prime, where their new numbers A prime and M prime are now relatively prime. So even if A and M original numbers are not relatively prime, we can take the GCD factor out, and then we are left with the numbers that are now relatively prime. Why is this true? So let me give you this one as a remark. So proof of remark. So first of all, since D is a common divisor, D is GCD of A and M, is greatest common divisor for A and M, so therefore is a common divisor for A and M. Since D is a common divisor of A and M, we can write A equals dA prime and M equals dM prime. So this part is almost obvious, just simply because D is a common divisor for A and M. Now, why can we say GCD of A prime and M prime is 1? Now, if GCD of A prime and M prime, let's say is some, for example, D2, which is bigger than 1. So if it's not 1, I can call it D2. Then what can I say? Then we will have A equals D. Now, then A prime, I can write it as D2, let's say, times A double prime. And M prime, I can write it D2 times M double prime, right? So if A prime and M prime have GCD of D2, I can write A prime and M prime this way, D2 times A double prime and D2 times M double prime. And hence, now if I replace this guy back into this guy, what do we get? We're gonna get A equals D times D2 times A double prime. M equals D times D2 times M double prime. And D times D2, which is bigger than D2, right? Bigger than D. Write this, and D times D2 will be a common divisor for A and M, right? Which is a D times D2 is a common divisor for A and M, and this is a contradiction with D being the greatest common divisor of A and M. D was supposed to be the great GCD of A and M, meaning that the greatest common divisor of A and M. But I found a common divisor of A and M, namely D times D2, which is bigger than D. So how come, if D is the greatest common divisor of A and M, how is that possible that A and M have a common divisor bigger than D? Then D will not be the greatest common divisor anymore. And D times D2 is bigger than D. Why? Because I was assuming that D2 is bigger than 1. Remember, basically, we wanted to show that D2 is equal to 1. So basically, of course, we are using a proof by contradiction here. So we wanted to show D2 is equal to 1. Then we said, if D2 is bigger than 1, then we will have a contradiction here, because D will not be the greatest common divisor anymore. And this shows GCD of A prime and M prime equals 1 as desired. Okay, now back to case 2.2. So what was the assumption in case 2.2? We are assuming D divides B and GCD of A and M equals D, which is bigger than 1. So our assumption is GCD of A and M equals D bigger than 1 and D divides B. So this one implies what? According to the remark, I can write A as D times A prime and M as D times M prime. And we know that D divides B. So I can write it as, so what do we want to solve? We want to solve AX congruent B mod M. So i.e. M divides AX minus B. Now M, so D divides B, so I can also write B as D, let's say B prime. So this is same as saying that, because M, I can write it as dm prime. A, I can write D A prime. B, I can write DB prime. So I can write it as dm prime divides D A prime X minus DB prime X. Now I can cancel D. Then I get M prime divides A prime X minus B prime. No, B is DB prime, so there's no X here. So B is DB. It was AX minus B, and this B I replace it with DB prime. So then I get M prime divides A prime X minus B. So please note that we can cancel D from both sides, of course, because it's very easy to verify, what is the meaning of dm prime divides this? Means this number can be written as this number times some k, for example. So you can easily write this in the form of an equation. And once you have an equation, so this number equals this number times another number, then you have D from both sides. And of course, when you have an equality, it's obvious that you can cancel a factor D from both sides as long as the factor is non-zero. And of course, this D is non-zero. So you can easily verify that we are allowed to cancel D from both sides. And this is same as saying that A prime X equals B prime mod M prime with, remember, GCD of A prime and M prime equals 1, right? So that's what we said, and that's what the remark said, that if A is dA prime, M dM prime, then GCD of A prime, M prime is 1. And the last congruence can be solved since as we have reduced to case 1. Remember, we already know how to solve a congruence as long as the GCD of these two numbers are 1. And right now we have a congruence where GCD of these two numbers are 1. So we can solve this congruence, but the solution of this congruence is same as every solution of this congruence will be solution of this congruence as well. So let me give you an example.